All right, so let's go ahead and get started. So, okay, so this is basically where we left off last time. So over here, right, we basically spent a bunch of time last class period talking about, well, about problems, right? Talking about problems, how they look, in the real world, where they're maybe more open-ended, where they're maybe more ill-defined, right? And so we talked about ambiguity. We also talked about faulty problems. And so we, had gone through basically a bunch of, types of problems, if you would. And the reason I want to talk about this stuff is just to give you guys a sense of what's out there. Um, kind of more specific than, oh, real world problems are more, complicated than, homework problems, right? Just, kind of a better sense of what exactly is out there. For those of you for those of us who, for those of you who just joined, go ahead and mute your microphone if it's not already, just so that we kind of keep the bandwidth usage in order. All right. So this is where we left off. Anything you guys have from the previous chunk of material? Otherwise, we'll go ahead and start on some new stuff here. If I don't see anything in text chat or voice chat, I'll assume everything is good. I like how Zoom made I had the chat open on my screen. All of a sudden, Zoom was like, "No, you don't need the chat. You can close it." Okay, so I'm not seeing anything from people, so I'm going to assume that basically we're good there as far as the last chunk of material. As just an FYI, there will be kind of another iteration of the slides. So there's actually on my end, there's a total of 60 slides right now. I haven't posted them all yet. I'll go back and update them later today. What's posted right now is basically the stuff that we did on Tuesday and then the stuff that we'll do today. But there are more as well, right? We'll probably be here a total of 3 days live before we go back to the videos. All right. So yeah, so let's take a look and see what we got, see what the next thing is. Okay, so this, right, hopefully is a bit of a question for you guys. You guys can think about, and maybe somebody can pipe up. Thinking about the homework, right, you've done in your classes, what do your answers look like versus what do answers, air quotes, look like in the real world, right? So what's the difference between when you submit a solution to me for the class versus when you submit a solution to your boss for give me a paycheck? What's the difference in those two things, right? So the answers you're expected to give, how do they look different? Any thoughts? I know, right, you guys, it's hard. You kind of have to visualize, right? You probably don't have a real job right now. So, it's kind of a visualized thing. Let's see, Ethan, what do you got for me?
I know, while like not ideal, sometimes if I can't figure out something or like I'm running low on time for one of your assignments or like assignment in general,
Mm-hmm.
I'll see what corners I can afford to cut, and like, so if one topic will lose me 2 points, another will lose me 5, I'll make sure I get the 5 done and just kind of sacrifice the 2.
Right,
Whereas that would be really bad to do at a job.
right. So in an academic, so you can triage is what I would say, right? So you can be like, oh, this is worth more. I can do this or
Yeah.
that. Versus for a job, you can do that, but you can't do it on your own, right? You need to come to your boss and say, hey, I'm out of time. If I have to prioritize, what are my priorities, right? You have to loop somebody else in. You kind of have enough information to do it on your own in a class, but in practice, you got to loop somebody in because you're not really the one that's defining, like what do I need at the end of the day? Because it's not just we'll do it and it's over for this week. It's going to feed into something else. And so your boss may know that there's another project that depends on your work later on, and that they need this component done, right? So if you're running out of time, focus on that. Don't do the other thing, right? Dan, what you got for me?
I would just say, just like we were talking about in the real world situation, sometimes there's a lot more depth to the
Mm-hmm.
things that you need to look into.
Mm-hmm.
And so your answers are going to be usually very specific to what you're being asked, but they're also going to be a lot more complicated and might require a lot more different groups input.
Yeah, yeah. So there's all sorts of additional complexity there, right? So one big difference actually in the real world problems, it's not talked about on these slides right now, because it's on the list. There is actually a massive list somewhere of stuff I want to talk about. But one big thing is sort of problem solving in the real world typically happens in the communication context of a group. You have other people, you have domain experts, right? So it's very typical, right, that if you're looking at a problem, you don't know the whole thing. You got to find the one guy who's an expert in this library to go solve something for you, to figure it out. You can't do it on your own without having years of accumulated knowledge. So typically, right, you have a group where you have a bunch of different experts coming together to solve something. That's what you need to do for really complicated problems. So that's a very, very typical thing. So yeah, like, so in general, right, your kind of your answers, right, aren't in isolation in the real world, right? They impact other people, right? You don't have full control over what makes the answer right. You also don't have really a good benchmark for knowing, are you correct or not? So here's another thought for you guys. You're used to having, you know, assignments be graded here. What is the sense of grading in the real world, right? So you guys get back points. What is it in the real world? Any thoughts?
Well, I know there's definitely no scale. It's usually like it works or it doesn't work.
It
If it
works or doesn't work.
passes, usually they have like a base case, or you know, things that it needs to fall under, and they'll
Right.
list on those statutes, and usually that's about it.
Right.
Depends on the situation. Sometimes it doesn't get, you know, there's no engineers going through and reviewing, make sure that all the, you know, the the boundaries are
Mhm.
set and are correct, and so, you know,
Right.
something that you do, you might kill somebody, who knows.
Mm-hmm. And so basically, there's kind of two ways your problems are evaluated in the real world. Is that on our side, engineering side, there are what they call acceptance tests, right? So there's some requirements, and then from that you elucidate specific, you know, things you can test, right? Specific metrics that can be evaluated, and then it's like, well, if I have X, Y, and Z, I can say that my answer is correct, right? So you either meet your acceptance tests or you don't meet your acceptance tests, right? But the important thing there is you need to actually have something to measure, right? You need to have the expectation of, under this situation, this is what I should do, or this is what the program should do. And then those should be, well, they should be sufficient for showing that your solution is correct, right? So there's the terms necessary and sufficient, right? So if it's sufficient, like if, as long as I show that it does this, then I'm good. I can accept it as being a valid solution, right? So there's kind of a necessary condition would be one that's like, well, I need to have that, but it's not enough to say that I'm good to go, right? I need to have sufficient evidence that I am complete. And then the other thing here is that kind of, this is more philosophical, is that even if you have acceptance tests, which may be in a sense giving you a Boolean grade for the work you've done, really your test is the trial by fire of going to the real world, right? So people can plan, do requirements, do whatever they want, but what it boils down to is when you pass it to the customer, right? How does it work for them, right? So that's the real grade that you're getting at the end of the day, right? We hope that our tests that we do as engineers are going to be sufficient evidence that we are doing this thing properly, but really it's not until it goes on to the real world that we really see how it performs. Ideally, right, we would be rigorous enough in our testing and evaluation to be sure of it, but we don't really know until we get it outside. And that's something kind of that Diego was starting talking about in Tech Chat, because he jumped to basically, you know, customer/employer satisfaction, right? How does it perform in the real world, right? That's our ultimate thing. It's not how many points do I get on a rubric, right? You don't have a rubric you can check off and be like, oh, I hit this and this and this. We need to see if it makes sense and it works in the real world. All right. So just some thoughts there. All right. So how does this kind of tie in maybe with courses? So in classes, typically when you guys do a homework assignment, you jump straight to design, right? So you give me an algorithm, you give me a description, you give me a solution to the problem. Typically, what you've produced is basically the design result, right? And I think this holds for most of the classes you guys take, right? If you're doing a programming assignment, right? So you're doing it for my class, you're doing it for, say, 205, right? Typically what happens is you write a bunch of code and you submit it, and then that's it, right? I mean, we can run it, we can figure out whether it works or not, but really all you're giving us is source code, right? If you did something like, for example, a bunch of sketches on a piece of paper, you wouldn't submit that to us, right? We typically just ask for that program result, right? We ask for the final design, right? And this is actually something that's very typical, I think, of university courses, is that they'll ask you it's basically implied. Give me the final result, give me the final design, right? And even in the technical courses we teach, right, basically what happens is we basically focus on technical skills, we focus on design, we basically have, you know, we're doing the work, if you would, right? Which unfortunately is really just one part of the picture, right? So in addition, right, to doing that, to writing that program, for example, there's kind of two other steps, right? So let's just think about programming assignments, because we've done those the most often, right? So in a programming assignment, your solution looks like a program. Maybe it's written in Java, and it is basically a design. I put together code in this way so that I implemented a linked list, right? That's a design. And that's all we talk about in lecture, right? Is how to design things. Really, there are two more steps, right? And then we talked actually, so this was actually a little bit mentioned in the handouts for the Module 1 maze assignment. But basically we have two other steps, right? So we have analysis and justification. So as we see in the previous slides, right, problems are, really hard to deal with sometimes, right? They have all these kind of ambiguities in them, right? They're like, I don't know what to do, right? I don't even know what an answer looks like. Really what we need to do is start with an initial step of analysis, where we look at our problem and we try to figure out what are all the issues with it, and then make them go away, right? And we can make them go away with assumptions. We can make them go away with the questions. And then we want to basically write down what is kind of our foundations, right? So if I don't have good foundations for what my problem is, I don't really have a good chance of solving it, right? I need to make sure that I'm starting from a position that is well-founded, right? So well-founded basically means that, like, what I'm building on works, is sound by itself, right? I'm not building on shaky foundations, right? So that's kind of a step that people maybe skip, right? Well, some people will skip, right? They'll jump straight to coding, and some of you, right, have actually been doing this, because this is, when you're generating that piece of paper that says, oh, I'm going to write this method and this method and this method, and these are what they're going to do, and this is what they have to, this is the code they have to have, and this is, the picture of how the nodes get added to the linked list. Some of you have already been doing this, right? But this, right, really is a standard thing, and it's a standard thing for any time you're faced with a real world problem, because they're so much more complicated than a homework assignment. Right? You can't just look at the problem statement and go for it. You got to know what you're doing first, right? And it's not really clear in enough specificity for you to be able to do a good job on it unless you sit down and analyze it explicitly. So that's one step. The other step here is justification. So another thing is that when you guys do work for a class, you typically don't have to tell me that it's like correct or that it's done, right? So we take care of sort of the evaluation of stuff, right? Really, right, you can think about this as you're working on a real world project, you solve a component of it, and then you go to your boss, you're like, hey, I did this. He's going to wait for you to say something else. He's going to wait for you to say, I did this because. And then you have to explain, right, to your boss, right, this is why I use this library because of this. I use this data structure because of this. You need to give some justification for why you did the things you did, because otherwise we don't know if you did the right thing or not. Right, and so this is something I hear from people, right? It's like they're going into a job setting, right? And they work on a problem. They have to explain to their team, this is what I did, and all of a sudden the team wants to know, why did you do it that way? And people aren't used to doing that, right? Because the thing is that it's not just a design that I think works, right? I want to know it works, right? A lot of times, right, I think there's this feeling of when you have work, right, it's good enough, right? Or I think it's good, right? And to me, I don't think that's enough. I think we want to be right, and I think we want to be right all the time. And I didn't have enough emphasis options in Excel to do it, but really this should have like all the emphasis options that you can think of, right? For me, I think it's important that we are right and we're right all the time, right? And this comes from the fact that maybe we're building things that really do need to work properly, right? So if I'm building stuff for a medical device, I'm building stuff for an airplane, I want to actually know that whatever it is that I built is the correct thing to be built. I can't mess around with a solution that I'm pretty sure works. I need to be right. I need to be right all the time, right? At least for me. Other people will have different lines here, and things are different. And always things are different in the real world, right? Well, I'm thinking in my head, I was like, yeah, I should probably have a discussion here about work plays or something like that. But like, yeah, things are going to be different. But for now, I want basically for you guys to start thinking about what does it take to argue that your answer that you give is either correct or is the best. And answering the question is the best, that's the hard one, right? So when we talked about sorting, when we went through like the lower bounds proof, that's the type of stuff you'd have to start thinking about. Like, how do I argue that my algorithm is the best thing ever rewritten, right? So don't even think about hiring somebody else. I'm already the best, right? Providing that argument is a very hard thing, but something that we'd like to start being able to do. So yeah, so these are our three pieces here, right? So we've done design in previous classes. Now we're saying we need to do analysis, we need to do justification, and these three kind of go together, right? Do my little arrows here. And this is where the acronym comes from, right? So you'll hear me say sometime ADJ. If you talk to people that work for me, if you talk to people that have taken 334, they'll know ADJ immediately. It's stuff that I've been doing in other classes already. It's new for you guys this semester, but it is in other classes right now. So yeah, so that's our basic model here, if you would, ADJ. All right, any questions, anything you guys got for me before we jump to the next slide? All right, let's go ahead and move forward. All right, so, okay. so you have to think, right, what happens when we transition, right? So at some point, right, you guys are going to go, right, you're going to graduate. It's going to be a wonderful day. You're going to be excited. You never have to go to school ever again. It'll be the best day ever, unless you choose to go to graduate school, in which case you'll be stuck for another year or two here. But, at some point you'll graduate, right, and you have to transition from all these academic problems to real world problems. That's kind of a tough situation. It's stuff that people aren't really used to, right? I mean, a lot of times, right, if you talk to people and you ask them, how did it go when you got your first job? Kind of the number one thing they'll say is, "I learned a lot." Right? That's always going to be a thing. Is they're always, I wasn't what I was expecting. I learned a lot. Those are kind of the typical things you hear from people that are getting basically a job for the first time, and they're referencing a whole lot of things there. When I was writing this, I was like, I meant it with regards to the types of problems, but actually, when people say this, they mean a whole lot of things. It's basically a kind of a rough transition. And even you start to see this when you go to capstone, right? So in another year, right, you guys will basically start signing up for SER 401, 402. You'll go and work on capstone. Capstone is going to be the first opportunity you guys have to work on a real world problem. There's going to be a sponsor there, and the sponsor will basically have a project they want to do. Like, for example, so I taught capstone one time. I remember some of the projects were like, for example, somebody wanted an automatic system to identify what type of ant they had. It was with the biology department. They have like a bunch of different pictures of ants. They want to classify what species it is. That's the whole set of requirements. Here's a bunch of ants. Right now, algorithm can tell me, what ant it is. That project took a lot of time and effort from those students. That was a machine learning project where they had to gather data, tag it, and then get someone to tag it for them, and then have some code to produce the labels for these things. Another project was like it was called Ping. I just remember the name of it, and it was basically just a really simple app for I can send people my current location, right? Or I can basically have like a kind of a group chat where we can turn on our locations and people can figure out where they're at. That was a simple one. And then I was actually meant for coupling with like delivery services, right? Or like Uber or something like that, where it's like, oh, I want to know, the thing that I ordered, is it on the way to me, right? Or is my friend, on his way to my house, like that type of deal. And again, right, it's sort of just a requirement of, write me an app that can let me securely view the location of other people that have agreed to see my location, right? And maybe make it a many to all thing, many to one thing, or many to many thing. And when people see those problems, a lot of times they struggle because they don't know where to start. It's not nice, like tell the expression of this function. It's very open-ended, right? I mean, you're not told anything technology. There's no methods there. I'm not telling you to implement an interface, right? You have to do it all from scratch, which is not a nice thing. And people typically in capstone, they kind of start to struggle with this, and it gets them a little bit better, right? You get a little bit more used to it, but then you kind of get hit full force with it when you go to the real world, right? And you go to your first real job. So a lot of times, right? These are some of the questions, right? I've heard, right? So a lot of times when people go solve these things, they first start by asking, where do I start, right? I'm not sure where I start. What do I do next, right? So you start to do some stuff, right? How do I proceed? And ultimately, am I done, right? Is this good enough that the customer will be happy? I mean, I could ask them, I say, hey, does this look good? And you give it to them, and then a week later it breaks, right? Because maybe there's a bug you didn't find, right? Or maybe they even come back to you and say, you know what? You misunderstood our requirements. You got to add some other feature, right? Again, how do I know when I'm done? So those are kind of the typical three that I've heard from people. Do you guys have any other ideas for problems people might end up running into when they're working on real world problems here when they're doing that transition? Any ideas? I just put it there. I don't know. I couldn't think of any other ones when I was doing it, so I ran out at three. Do you guys have any other ones that might be big questions that people have? I'm trying to think if I can think of any more. These are the main ones I've heard like just a lot.
You're talking about like the ones you have.
Yeah, like what keeps people up at night when they're forced to do real world problems? What is that they're thinking to themselves? So I have three examples there, right? You keep on wondering, how do I get started, right? You don't know how to do it. Are there any other questions that people might have when they get started?
I think for me, sometimes it's, am I covering everything
Yeah.
in the scope of what I need to do?
Yeah.
Or am I missing something?
Yeah. Let's see. I'm going to write coverage. I don't see a good way for me to put text on here. Coverage. Okay. like normally, right, you'd have like for us, right, you have a rubric, so you can typically look and be like, oh, am I covering everything or not, and then you can go to bed and get some sleep. Not so in real world problems, right? In a sense, you maybe want to think about generating your own rubric. All right. So quick writing thing here, right? So hopefully you guys can write on my screen. So we have the letters, right? A, D, J. What do you guys think for the first question here? Is that most associated with analysis, design, or justification? You guys can just write the letters on my screen. What do you guys think? I got to do this writing thing so I know everybody's alive and well and hasn't fallen off the face of the earth. What do you guys think? Write one letter over here kind of next to that first line. What do you guys think it's most associated with? Analysis, design, or justification? When I say associated with it, like which one of those would help us to fix that problem that we have, right? So if I don't know where to get started, what will help me with it? Analysis, design, or justification? Any guesses? Okay, so I got a bunch of A's there, and I also got, okay, I want to see if I get any other weird letters there. Bunch of A's there. So yeah, analysis, right? Because the thing is, in analysis, you're basically having to lay out, what do I know? What do I have? Where do I need to be, right? So analysis is what I need to do in order to get an idea of where do I start. And also it's a mechanical thing, right? So sometimes you look at a problem like, I don't know what to do. Well, analysis basically says, start by laying out what you have, right? So it'll give you a little bit of work to do. And as you start to work to things, you'll have a better idea of what to do next. Okay, let's see. Second one, what do you guys think for the second one? A, D, or J? Which one is going to be most widely associated with it? So D, what do I do next? Okay. So here, yeah, so here I'd actually say it's a little bit of a mix of analysis and design. All right, so I'll put all right, so I'm going to write over here, let's see, I'll put A plus D. And the reason is that this over here, I don't have much brain space. Somehow there's always this idea of, let's say you have a starting point, right? You're trying to solve a problem, you have a starting point, and then you have different choices, right? I could do this, I could do this, I could do this, right? So you have that. What do I do next, right? So this is your design, right? You start with trying to do something, and then you update it, and you want to do something else, right? And then maybe update it and do something else, right? Something like that, right? That's your design flow, right? So that's your design going on there. But then you also do need a little analysis because you want to know what's valid, right? So can you do, you can take this action versus this action versus this action versus this action, right? You need to know the valid moves, right? So that's kind of founded on your analysis, and then your design is where you're like, okay, I have these different options. Let me pick what to do next, right? And try something and see if I can get something a little bit better than what I had to begin with. So it's a little bit of a mix of analysis and design. All right, last one there. Am I done? What do you guys think? A, D, or J? V. Yeah, those look like V's, guys. Those don't look that much like. That's only like honestly, you guys' handwriting on the computer looks like my handwriting on the board. Sorry. Yeah, so that's all about justification. So am I done yet, right? I want to be able to justify that my solution solves what I set out to solve, right? So yeah, that's literally justification there, right? Making sure that we've done the proper thing. And obviously it's more difficult than in a class because we don't have a good metric to decide, are we done yet or not?
I have a question.
Go for it.
With am I done? I know like with certain projects you can continually update it and update it and update it.
Yeah.
When do you stop updating a project, or
when do you stop updating a project?
Like,
yeah. So there, I mean, the immediate answer is when you're no longer paid to do it. Okay. So one of the problems in software engineering is that, and this is the same, right? They say the only thing you know for sure is your requirements are going to change, right? So the problem is this, right? You will basically have over time changes to what's expected of your software product, right? So people see the market changes, they want this new feature, and then all of a sudden you need to go and update it and do some new things. That's sort of, I mean, it's going to happen. That's the one thing you kind of can depend on. Generally what I think of is you kind of compartmentalize this stuff. So you don't want to end up basically chasing, the carrot forever, what you want to do is basically draw a line in the sand and say, okay, these requirements are what I'm doing, right? So I will try to solve the problem for those requirements. I'll try to justify my answers for that requirement, and then I'll call it a day there, and I'll say that I've completed this iteration, if you would, right? So sometimes, right, you have this kind of notion of an iterative development where it's like, okay, we have these requirements, we're going to do our best to fulfill them, right? That's our gold standard, and then, right, we may have to do it again, right? And it is kind of gonna basically be a live process. So maybe if I was drawing a little picture here, right? Let's see if I can draw over here. Where's my pointer? You can imagine, right, there's a loop where these are software iterations. Where you have to do your analysis, design, and justification. And this is for some feature set. Some feature set. There you go. Right. And your justification tells you when you're done with a cycle here, right? Tells you when you're done with that. But then ultimately it's going to be left up to your customer for how many times you repeat this cycle of trying to build out something that works, right? And again, right, it does actually really boil down to when they stop paying you, right? But yeah, because there's not really a never-ending thing. There's just kind of milestones along the way to hit that you think you're done there, and you cross your fingers that it's not too soon before they turn around and add a requirement or change a requirement on you. Yeah, all right, good question. All right, anything else you guys got for this slide? Otherwise, we'll move along. Okay, let's move forward. All right, so just kind of a quick discussion here. Somehow there's this sense, right, the real world problems are more difficult or harder than academic problems. Now, in terms of problem hardness, we've actually mentioned this once before, right, or difficulty of a problem. We've mentioned it when we talked about analysis of algorithms. So when we did analysis of algorithms, which is way back in module 4, right, that's where we did like the big O stuff. We basically had this idea that some problems are rather easy to solve because they're efficient, right? So they don't take all that much time to solve, right? I maybe have just a couple nested loops, and if I put an input into it and I run it, it'll finish in a reasonable amount of time. And then we talked about hard problems, which basically were ones that run in exponential time. This whole picture, right, in terms of analysis of algorithms, right, and we're saying, easy problems are ones that take, a short amount of time to run, versus hard problems are ones that take a long time to run. This is sort of, well, it's orthogonal to all this stuff here, right? So it's basically, talking about, how algorithms work, right? So algorithms themselves, problems themselves can be kind of hard to solve computationally, right? So the problem, right, of that UPS driver trying to deliver every package on his route in the shortest amount of time, that's a computationally hard problem. It's not necessarily a problem that's, ill-defined or a problem that's open-ended. We can fix both those things as long as we write a problem statement in a very concise and sound way. So it's not difficult in that sense. It's difficult in the computational sense, right? So this is kind of a different idea. And I think, let's see, do I have I meant to put in basically the keyword here, computational complexity, right? So this is kind of a different sense, right, of difficulty, right? So even if your problem is very well written, basically the solution you might want to generate for it could be a solution that will take forever to run, right? Which is basically no good. When we're talking about how long a program takes to run, we usually use the word hardness. So say the program is hard, air quotes, if it takes a really, really long time to run, right? And then above that, we basically also have another category, which is intractable problems. Those are problems that are just, straight up, impossible to do. So maybe as a little chart over here, right, it's typically where we have things that are, quick to solve, right? So I can find something in an array really fast, right? So those are things that are polynomial time. Then you have things that are non-polynomial times, and then you have things that are intractable, right? So this is kind of a different way of looking at how hard something is. This is computational complexity. I'll put just CC here, rather than this whole real-world ambiguous problems thing, right? This is just difficult in terms of running the numbers, right? So this is kind of a different dimension here. And the unfortunate thing, right, is that typically if you look at this in terms of what people will pay you to solve, these are the ones you get $1 for, these are the ones you get a couple dollars for, and these are the ones you get a lot of money for. So unfortunately, right, the problems that are mathematically or programmatically hard to solve are the ones that are worth more. If you go back to our previous chart where we had like the two axes and you try to basically look at, hey, how much money do I get paid for solving these? What you realize is that the money all lives in the area where those ill-defined open-ended problems are, right? Those are the ones that people pay for, not the simple ones. So yeah. All right. So that does it as far as our section on typology of problems. So that was kind of a little bit of a review. Oh, not, I don't know if it was a review or not. I'm not sure how much of that you guys have seen before. If you guys are bored, I would actually be really interested in hearing how much of that you guys have maybe seen in other classes or not seen. So that kind of though wraps up our first section, right? So first section is on typology of problems. The next thing we got to talk about is introducing these ADJ steps. So before I go forward, do you guys have anything on the previous slides we did the types of problems?
The only thing is you're starting to garble a bit again.
Breaking up a bit again. Okay. Let's see. I'll pause for 1 second then. Any other questions, comments? Okay. So let me move forward, and I'll talk for a second here. Maybe that'll get me past the your voice is breaking up part. So what we've done up until now is basically talk about the different types of problems that are out there, right? Kind of get a feel for where our stuff lives versus what real world problems live. And so what we'd like to do, right, is basically try to mature our skills a little bit to be able to handle more complicated problems. Right now, we don't really need some of this stuff because the problems we're working on are fundamentally educational problems. They're straightforward, so you don't need to spend time, analyzing them or justifying your result. But the problem is you're going to need that later on, so probably it's something we should start right now. So that's what we're going to do in this first section. So we're going to basically talk through these different steps of ADJ. And we're basically going to do kind of two different little examples. So the first example is going to be something really simple. It's going to be basically trying to pick the data structure for a problem. And then later, we're going to actually do one about adding a new update function to a priority queue. And we'll talk about a whole bunch of stuff that's maybe more rigorous. We're going to talk about things like proofs of correctness or proofs of terminations. We're actually going to use some math stuff for a little bit or some logic stuff for a little bit. And yeah, then we'll be, and then I'll be basically our module. I still basically need to update the slides on Canvas. All right, so let me clear my drawings really quick and we'll go for it. Hopefully my voice is got a little bit better there. I was trying to stall for a little bit, right? Got to vamp for a bit to see if the data will fix itself. All right, let's go forward. So ADJ. So we're going to define this, well, we're going to define ADJ as follows. And I think I'll probably just read these from the slides because I was happy with my definitions when I wrote them. So we'll say, right, that we want to basically aim to do these three different things when we're faced with a problem, right? And it could be any problem. It could be something that's really simple, like a homework problem, or something more difficult, right, like a real world problem, right? We kind of want to have something that we can apply in either case. So our first kind of stage here, right, is analysis, right? So we want to basically look at we want to provide a translation of the original ill-defined problem into concrete requirements that can be evaluated, right? So I need to know what's going on, right? A lot of these problems you've seen, right, it's not really clear what they're asking for. And so you got to sit down and figure it out, right? Perform some sort of analysis. Typically, this will be where you spend most of your time compared to the other two steps. Second thing here, right, is design a solution to the problem being solved. This is what you guys are used to doing. This is when you guys, do a homework assignment and you type up a bunch of code, right? You're giving me a design, right? This is how I can solve the problem. And then the last one, this is the one that kind of can be easy or hard depending on your previous two steps, is providing a justification, right? An argument that supports your design as being superior to other potential designs which also satisfy the analysis requirements, right? So you can imagine, right, maybe, again, right, you're at a company, right? Maybe you're at a company who is bidding on a project, right? So sometimes, right, like the government, right, maybe has a project they're trying to open, right? They may have a call for proposals. A bunch of different companies are competing for this one call, and maybe you need to develop a prototype. Well, somehow, right, in order for the government to give your company all this money, right, for them to be like, okay, of the companies, that could solve this problem, this is the one I'm going to pick. Well, the way you get your company to be on the top of that list is by being able to justify, hey, we're the guys for the job, right? Our answer will be better than other people's, right? That's part of justification, is being able to show that your answer is superior to other options. And you want to do that because the person with the best answer, right, is going to get the money, right? So whether you're a company getting a contract, whether you're an employee getting a job, right, you want to show that you're better than other people so that you can be picked to work on something, right? So we need to justify that our work, right, our design, right, is superior to other options, right? Rather than it just being like, oh, I think it's okay. We want to be able to justify beyond any shadow of a doubt that it is indeed the right tool for the job, right? It is the right thing, right? This is as good as it's going to get, right? So that's going to be a kind of our end goal. All right, so these kind of pieces are all kind of related to one another, right? So first, we basically want to show, right, that we have some analysis, right, call it A, and this analysis yields a design, right? So from whatever I picked out, right, I get a design that makes sense, right? Assuming that my analysis is good, that basically means that my design will be well-founded, right? I'm building on things that I'm pretty sure are correct. And then when I basically need to argue that that design is optimal, right? And optimal can mean a whole bunch of different things. We'll go into that. So we want to argue basically that my design is optimal. And then justification. Justification is an argument, or sometimes you'll even call it a certificate, that the design is indeed optimal, right? So these are kind of, these all kind of go together, right? We build on analysis to produce a design, and then the analysis also can kind of help us to justify this design is the best, right? And the way I say it's the best is sort of in justification, right? I say, okay, this is what's important in the problem, right? My analysis said it's important to do X, Y, and Z, and then my justification says, oh, I did X, Y, Z. Those things come together, and therefore, right, my answer, my design is, the best, is the optimal one. So yeah. So our basic plan is to take a look at a simple problem, and it will be really simple. I'm gonna kind of go through each of these steps, and we'll talk about a whole bunch of things. Eventually, I'll post a solution to it for all of you guys. I'm gonna basically post 2 kind of example problems that are worked in this style, so you can guys see what we're doing. One of them is posted right now. It's actually we'll probably won't get to today. We'll probably get to it next week. But there is one example already you guys could look at a little bit. So yeah, so we'll take a look at that. We'll talk about some problem-solving techniques as well. Somehow the idea here in this in this slide deck is to introduce these 3 different steps, if you would, and then we basically will maybe add problem-solving techniques as we go through them, right? That's the plan, right? But first we got to start with a framework, right? We need a framework, and then we can fill in the framework. All right. So questions, or I'll move forward. Hopefully people are okay. I'm trying to get through more slides than I did the other time. The other time I felt like I didn't get through that many. All right, moving forward. So as an example, we'll take this here, right? So this is going to be in double quotes. Consider designing a program where you need to store a fixed collection of items and display them. Would you use an array or linked list? Justify your answer. So we'll use this kind of as a model question. It's a little bit ambiguous. Maybe I'll ask you guys about that in a second. But it is one kind of that's typical, right? So I think that even one similar to this showed up on the prerequisite check exercise you guys did the way beginning of the semester, if you guys remember that. So it's something similar to that. So this is our question here. And for us, right, so we're still kind of in the context of a class. For the sake of learning this stuff, we'll typically attach this little block to the end, right? So if you get an ADJ question, right, you'll see this here. It'll say analyze the problem, design a choice, justify the choice. You guys at some point will basically see what our tag as ADJ problem sets. So normally you guys have short answer programming, all that stuff. It is what it is. Occasionally you'll see a problem that basically is tagged as being ADJ related, and that will have kind of these 3 different steps that you'll need to perform if you're solving that problem. So typically, right, basically this kind of part will go away, and then you'll have this kind of 3-parted thing at the end instead, saying that you do those steps. Now for this is a relatively easy problem. Well, yeah, it's a relatively easy problem. Part of it comes from the fact that your design is really just a choice, right? So notice it says there on the bottom, design a choice. That means your design, air quotes again, is either an array or a linked list. You don't need to give code for this, right? So some people see this and they'll start writing code. Don't do that. That doesn't have to do anything with the problem. The problem is just, do I pick an array or a linked list, right? It's a kind of a very, very different feel. So yeah. But anyways, we'll work with this kind of as our sample problem. And if you were assigned this, right, as a homework, right? So I could assign this as a homework assignment, but I won't. I'll give you guys a sample solution instead. If you do assign this, right, you'd probably do this as a write-up, right? So a lot of this stuff ends up being written. programs are nice, right? But they don't really let us say everything that we want to say, right? We need to have a good kind of verbal way to explain what's going on, right? So probably things would be probably if you were answering, sorry, to be in form of a write-up. All right, and so I have here one quick answer for it. And so let's see. I'm going to ask you guys. So okay, so you guys can see the question is over here, right? This is the question over here. What do you guys think about this answer? Do you guys think good or bad? So if you guys want to, you can either maybe, write over here. You can put a check mark whether you think it's good or bad. Good or bad. I don't know where bad came from. I'll fix that typo. Good or bad. You can put a check mark there, right? One of the sides. Think you say put it to indicate if it's good or bad. And then really, it'd be good if somebody wants to speak up and maybe explain why they think it's good or bad. So take a second, look at that. Give me a check mark on the screen whether you think that's a good or bad answer. And then if you guys have a voice chat, I'd like to hear, maybe some explanation for why it's either good or bad. So yeah, what do you guys think? Okay, so we got a few votes for bad. Okay, anybody want to tell me any problems they see with this answer? Any explanation for why it is bad? What do you guys think? Yeah, Tom, what you got?
Well, the problem doesn't say that it needs to be able to add or remove elements quickly.
Right. So here we're missing an alignment, right? So this by itself, right, is a true statement, right? A linked list will allow you to add or remove elements quickly, but there's not really anything in the problem prompt that says you need to add or remove things. So this isn't even lined up, right? So you're kind of lost from the beginning. So this is not a good answer at all. There's no alignment, right? So you can imagine, right, normally, right, you want basically your answer to follow from your question prompt, but that's not the case, right? This here is broken. So hopefully that's something that if you guys, so like the problem here, right, is that this is a true statement, right? So this is correct to say that a linked list will allow you to add or remove elements quickly. The problem is it just doesn't matter for us here because we're not dealing with adding or removing elements, right? We want to display it. So this is just weird. And unfortunately, this is actually the answer I got from a few people on the prerequisite exercise. So I gave a related one about storing a fixed size collection. I had several people say use a linked list because you can add or remove elements quickly. That's not a good answer. It simply doesn't follow from your premise, right? The idea of I need to display a bunch of things, it just doesn't follow. Okay? So yeah, so this is not a good one, right? It by itself would be a correct statement, but it's not a statement that's built on what we have, right? So yeah, so there's a sense basically of soundness in a problem, right? How well things go together. So over here, right, we have my soundness slide. So basically, right, we want to make sure that when we have an argument, right, and in a sense, a design is an argument, a justification is an argument, right? We want to make sure that each piece of it builds on other pieces, right? We don't want things to be disconnected. That's exactly what we just saw, right? So now, right, usually there's kind of two problems we can see, right? Two things you can break, right? Either, right, you have your argument itself, right? That might break, right? So in your description, right, that might be incorrect, right? You might say, this and that and this, right? And all of a sudden, one of those doesn't carry forward, right? One of them doesn't build on the other one. Or it might be that you started working on something that was bad, right? So maybe you worked under the misimpression of how a linked list works, something like that. So you can have errors either within your argument or what you're building on, right? Normally, right, you kind of expected every kind of piece of text you write when you're explaining something, right? Every idea you have basically is linked to everything else you've done, right? It's not just kind of in the void, coming from the void, right? Which is what that previous answer had, where it answered something that wasn't really relevant, right? It doesn't make any sense. So to emphasize this over here, answers must follow from the problem statement, okay? This is a big thing, and this is something that if you're like, in general, I would expect it. On the ADJ stuff, you absolutely have to do it, right? And somehow, right, this is something that maybe comes up a lot, actually, in my classes that I see a lot. A lot of times, right, people actually do the thing we saw on the previous slide, where they did something that doesn't actually, build on, the question that was given, right? I see this a few times. I'm trying to remember an example from, for example, like operating systems. Okay, I'll just give you guys this as a quick example. So one of the questions I've given in operating systems, my other class I teach, is I say people, pick a system architecture for an operating system to run on a calculator, like for example your TI calculator, and you have these different choices. It can be you can just hack it together. It can be modular. It can be layered. It can be hybrid. It can be. And I give them a list of options. So imagine that, right? This is the question in my other class. And I asked them for an answer. And people will say something like, I want to choose, I will use a layered architecture to build the operating system for this calculator because it'll make it more secure. Does that make sense? What do you guys think? I'll put a yes or no over here. So if someone is basically trying to explain, like without even knowing, right, what those architectures are, right? Does it make sense that someone would say, I'm going to choose this design for a calculator because it needs to be secure? Does that make sense to you guys? So yes or no, what do you guys think? You guys can vote on my screen for a second, right? So again, think of the example, right? Picking an operating system design for a calculator. I mean, you don't even need to know what the designs are, right? There are a bunch of different choices. Does it make sense that I would say, I'm picking this because of security? So I get some marks there on the no side. Yeah. So yeah, again, it's something that doesn't really follow. Because wait a minute, it's a calculator. Does your TI-84 need security? Probably not. Because that calculator, right? I mean, it's not connected to the internet or anything like that, right? There's nothing in the prompt to say this is an internet accessible thing. It kind of just is a calculator. So again, that kind of doesn't follow from the original one, right? So yeah, that's a little bit sketchy, right? But that's something that I see, and again, I see a decent amount. Maybe a third of the class gives you an answer that looks like that. That doesn't follow from the beginning. And like, it kind of makes sense because they'll say, oh, layered, and then it's true that layered is a little bit better at security, but it doesn't matter in terms of your problem, right? Your answer needs to follow from the problem, otherwise it's not a good answer. Okay? So yeah, so that again is another thing. Put as much emphasis as I can on the slide. That's a big thing. And I know, right, people I think may think that they're doing this, but they're sort of not, and it's essentially by accident because they skip the analysis portion of asking what is its valuable, right? If you sit down and analyze what does it mean to write software for a calculator, you realize that nowhere in your analysis does security come up because the thing isn't even online, right? I'm not going to change software on it very often, right? It doesn't come up. So you skip analysis, though, you don't see that, and then you put it by accident. All right, so let's see. So we have some stuff here. We're going to do, I guess, a little charty thing here. Okay. So we have a bunch of different examples here. I don't know if I'll do all 5 of them. We'll do a few of them, though. I was trying to come up with just stuff to talk about there, examples here. So soundness, right, again, means that everything kind of follows, right? Things flow together logically. What do you guys think about these, right? So the first one says, right, these are other basically sample answers, right? What do you guys think about the first one? Would it make sense? Does the first one make sense? Okay, so we're saying that this is a potential answer. Linked list because it will allow you to add or remove elements. Is this sound or not sound? What do you guys think? Put a little mark there under yes or no. The chart's now on the right-hand side of the screen. What do you guys think? Yeah, it doesn't make sense. Doesn't make sense, yeah. And this is kind of, exactly what we were talking about before. It's like, how does add and remove elements have anything to do with what I, am asked to do, right? So that's not sound, that's a mess. All right. So the second one, maybe a little bit trickier. Linked list because it'll allow you to quickly access each of the elements. What do you guys think? Good or bad? Okay, so I have some people saying yes. Okay, so this one I would say is sound, but it's not complete. Because in our question, this is going to sound so picky, I'm sorry guys. In this prompt, it says to display. It doesn't necessarily say to access the values, it says to display them. It's implied that they're being accessed, right? I need to access and I need to display it. right? So right now, right, we're good with what's up there, right? But it's not quite complete enough, right? So yeah, so we'll have it as sound, right? But it's sound, but it's not quite done yet. Okay. All right, third one, linked list, because it'll allow you to quickly access each of the elements. Is this sound or is this not sound? I'm wondering if it's just one person using a heart or whether it's different people using a heart. I may never know. So some marks there, right, on either side. So this one I would lean towards it being not sound, right? And it would be not sound because, wait a minute, this is a linked list. Well, I can't just jump to an arbitrary element in a linked list, right? And that's kind of what this is implying here, right? Because you're saying quickly access each of the elements, right? That means you're basically going to go and potentially, jump to a specific element, right? Linked lists definitely don't support that. Now, one thing I do want to mention here is that this quickly access is actually a little bit of an ambiguous term, right? So quickly access, say QS, right? This can actually mean one of two things. This could mean that you want random access, rand access, or it could mean looping access, right? All, right? So what quickly access is doesn't, I mean, also, what does the word quickly mean? Maybe that's in doubt. But I could basically be referring to random access versus just having to look at each thing in turn, right? Random access, right, if I'm looking at that, right, then obviously it's not going to work for the linked list because it's like, well, that linked list, I mean, I need to navigate through, right? It's going to be terrible. So yeah, anyways, that third one, right, is not sound. Third one, so the fourth one there, array, because it allows you to quickly display each element. Is that sound? What do you guys think? All right, so I've seen some check marks there. So yeah, that sounds a lot more reasonable to me, right? I mean, in an array, right, and now, right, it's right, if I'm doing random access or if I'm doing it in a loop, either way, I'm able to get that stuff quickly, right? So that should be good, right? So even though there's actually a little bit of ambiguity in that prompt, because we're talking about arrays that can do either, that's actually going to be good to go. So that one's fine. All right, last one. So number 5, what do you guys think? Sound or not sound? And this one, I think it's kind of going to be important for our definition of quickly. Well, it's for our definition of what display is. Are we displaying them randomly or displaying them all, right? So here, it kind of depends on what we mean, by display. I mean, display actually could even have more stuff behind it, right? So it's like, well, do I display all of them? Do I display some of them? Do I display a specific one, right? Here, right, the problem is we don't really know that. Our linked list, right, we could probably loop over it pretty quickly, right? That would be fine. But if we're asked to basically pick out an answer and then display it, that will be really slow, right? So this last one, I would basically say could maybe either fall into either of these categories. The problem is this needs to be a little bit more well defined. Over here, quickly display, it doesn't really matter for array because it'll be fast either way. For a linked list, it does matter. Okay, so I would say it could maybe go on either side. Okay, let me put my dot over there. So yeah. All right. So let's see. What do I have for my next point there? All right. So we did a bunch of those examples, right? So the problem is, right? Maybe you get the sense, right, is that even though things can be well written, in kind of the grammatical sense, they may just not make sense, right? They may not make sense in the context of the problem that I'm solving. They may not make context in what I know about it, right? So here's a little bit of ambiguity that does hurt me. Okay. So last question. So just a thought here. Maybe we can get somebody to speak up on it. So if I think about just writing an answer, right? So I'm asked to solve a problem. I'm writing an answer. Do I want to have a longer answer or a shorter answer, right? Should I have more or less raw text in it, right? So these are all pretty compact answers. They're all about the same length. Just in general, if you were writing an answer for something like this that needed to make sense, should it be shorter or longer in general? What do you guys think? Any thoughts? So I see one heart on more. So you guys can either throw a little icon there on the screen, or if you want, you can speak up. It'd be nice if people speak up. I don't want to be the only one talking here. So some votes for more. Can anybody want to? So I think that's okay. Okay. Now we're getting the less crowd in there. So we got some for more, some for less. Anybody want to be a tiebreaker or come on and talk about it a little bit? Jacob, what do you got for me?
I think that it might be useful for an answer to have more text in it, just to give you a little bit more freedom to better explain what you mean by things like quickly access or quickly display.
Yeah.
So just to give you more of an opportunity to explain yourself.
Okay. Yeah. So if you like, so I've done some of these problems right in my other class 334. Sometimes the answers can be, I mean, sometimes an AAJ question will take 10 pages to answer, but that's because those guys that did it were kind of crazy. Here it's sort of, there's a little bit of a fine line. Anybody else want to put in on this, or otherwise I'll talk through it a little bit more. Dan, what you got?
Well, you should always explain what you're trying to do, but you should use engineering report, not a novel.
Engineering report, not a novel, right? So there's a sense there of whatever it takes to do it well. Okay. Let's see. I think there was somebody else too, right? Dan, what you got?
Yeah, wouldn't you also determine on like how specific the question is? Like if it's a very drawn out question and it's extremely specific, then you don't need to put a whole lot of text in there.
Right. So it depends on how much work there is for you to do, right? How specific it is. So generally, what you always think about is what do I need to do a good job? So some questions are simpler, less text. Some questions are more complex, more text. What you don't want to do, and what I've seen people do in the past, is they just try to talk about everything, right? So if you take a simple question like this, right? So you can imagine, right, this question here can probably be answered in a paragraph. If you write me a 100-page novel on it, that's probably bad, because I'm going to find a bug in there somewhere, right? If you're too verbose, you've left more places for something to go wrong. So usually what it is you want to be minimal in the sense that you do what is required, you don't do extra, right? So sometimes people fall into the trap of, the teacher is going to ask me, wants to know exactly how this works, so I'm just going to write. Don't do that. Don't write the novel. Just write what is actually required to get your point across in a way that makes sense relative to the complexity of the problem that you're working on. Okay? Don't go overboard with it. But usually, a lot of your space is spent on the first part, the analysis part, and doing the analysis and the definitions of making sure, I need to make sure that I eliminate all my ambiguities. That's actually kind of the first thing that people said, right? Is that you do need to spend some text, like I was saying, in the beginning, right? Just because you need to make sure that you're coming from a good place, but don't do more than is necessary. Right? All right. So you got that. So let's go ahead and move forward. So just a quick discussion here about process and a little bit about patterns. So for you guys, right? You guys are engineers, right? Probably at some point you were, confronted with the question: do I want to be in engineering? Do I want to be in computer science? And if you ever, went and asked people for that, probably the main thing you heard was that engineering is all about process, right? It's about doing kind of things in a regular sense, right? I do X and Y and Z, and then I do X and Y and Z again. I have some sort of instructions, right? Almost like an algorithm that I am following again and again and again and again. Let's see. Okay, so hopefully, right, you guys have used a process at some point, haven't you? Question mark. This is a question for you guys. If you guys want, you can write an acronym on the screen. There's usually one particular process that people have used before in the past. Have you guys followed any processes in your other classes? Put a box off the side here. Come on, let me draw. Have you guys used any processes? Have you been asked to follow any processes in another class? PSP. Okay. PSP. A star is a process? Okay, so star is not a process. So yeah, so personal software process, right? Also agile, right? Scrum, right? There's basically kind of a little set, right, of these things that we teach you guys. And there are kind of ways to, manage what it is that's going on, right? To make sure that things go smoothly. I think the first time people see process is in SER222. Typically there people learn PSP. As you guys go forward in the process, in the program, you'll learn other things. So once you're done with me, right, you'll get to go visit Alex in SER315. You'll learn a whole lot more about processes. You'll basically be asked to do Agile. You'll be asked to do Scrum when you get to 315. And when you get to Capstone, you'll do one of these as well, right? You'll have a development process. Only there it could be anything, because it'll be defined by your project sponsor. Project sponsor will be like, oh, you should use Rational, right? And then you have a different process that goes on. So yeah. So use of process, right, is one big thing that basically distinguishes engineering from computer science, from math, from a lot of other domains, right? It's one of the things that makes you guys special. All right, and then I was talking to somebody the other day and about the differences between engineering and other stuff. So I put in this other little bullet point there. The other difference between engineering and a lot of other disciplines is the idea that engineering is ultimately about control. It's about, you know, bending the world to your will, right? There is this problem, I'm going to solve it, right? By changing the things around me. That's one of the other big things about engineering. Now, I don't think they typically ever say that, which is weird, but that's what engineering is about. It's about control. Versus about science, right? Science is more about discovery. It's about understanding. All right, we got some questions here. Maybe we can talk about. Okay, so the first one we'll do is a yes or no. The other ones, I want to hear people. Come on, I want to draw. Let me draw. There we go. Y and are we talking about using a process here? In the past few slides, are we talking about a process? Yes or no? What do you guys think? I'm erasing the persons off to the side. All right, got some votes for yes. So yeah, we kind of are. We're defining 3 different stages: analysis, design, justification, and we're saying this should happen in sequence. Now, I don't know if they're gonna, happen. I'm gonna be done with analysis, then go to. I'm gonna have to do some backtracking, right? But in general, I do these things in this order, and I always want to do the same things. I don't want to, for example, look at a problem and skip analysis and jump straight to design justification. I want to make sure I always do the same thing. So this is actually a process. So I think I used the word even a couple slides ago, and I probably should remove it because it was a bit of a spoiler. ADJ is a process. Okay. So yeah. So next one is, so these two are, hopefully we can get some voice chatter here. Why is using a process good? Why do we follow processes? Why do we even bother with PSP, Agile, Scrum, ADJ? What is the point of using a process? Any ideas? Hopefully you guys got told something in 216, because if you're doing PSP and you're like, I don't know why we're doing PSP, that's a problem. Why do we want to use a process? Why is the process good? We'll go to Jacob.
Well, I mean, I guess the way it's kind of explained at 216 is that the buck basically stops at the programmer in determining the quality of the software.
Yeah.
So just to have a set of steps to help you, stay on track and help you to produce good quality software.
Okay.
It just increases the chance of making good software as opposed to just sort of hacking things together.
Okay. So overall, it improves quality, right? By for example, there I think it's managing the software engineer's time, right? That might be one thing. Dan, I think you had your hand up as well. Do you have something?
I was pretty much on those lines, yeah.
Okay. Let's see. I think I see something from Hannah in text chat. Hannah says, it helps to ensure good software and also planning and production time are better estimated with a process. Okay. So a few things here. I'll try to unpack a little bit. Joseph, you got something to add? Yeah, you're muted on the mic, Joseph. If you want to talk, you have to unmute yourself.
Oh, sorry. Yeah. So if you if you have a process, you have a structure, like a structured way of doing things that makes you more productive.
Structured way of doing things that makes you more productive. Okay. Good. So let me add a few things here. First of all, is reproducibility. You don't want to do a good job just this week. You want to do a good job next week and the week after and the week after and the week after. The way you get reproducibility is by doing the same thing over and over again. That's when the process gives you. A second thing is that if you have a process, you have the idea of analytics and prediction. So I'm doing stuff in a certain way. I can start to figure out, how much time it takes to do me. That way I can have better estimates for the future, right? Which I think is something you guys maybe started to do in 216, right? We want to have some predictive capability. We want to know how much work we can get through. We want to be able to, in a sense, predict the quality, right? So it's like, okay, it took me this long to do this and to meet all these test cases. Therefore, next week, if I want to make sure I'm doing the same thing, meeting all my test cases, I need the same amount of time, right? That's how we get quality, right? And then over time, right, we can basically kind of figure out what works for us, right? And then, then we get the kind of the reproducible quality, right? That we're always going to do a good job, right? That's what we want in the end, right? Is to always do a good job. All right. So reproducibility, consistency, predictive power. And there's something else there about, well, regularity will buy a lot of things. Regularity is kind of one of your tools when you're dealing with something that's very difficult, right? So sometimes people follow a process because the thing is, you follow a process, it's like following an algorithm. You're going to have a good result at the end, right? So if you are looking at a really intimidating problem, one that scares you, like, I don't know what to do, just follow the process. Trust in the process, right? It'll get you through, right? It'll help you break into pieces. It'll help you tackle the pieces. It'll help you get through it, right? So whether you're looking at something that's really hard, or maybe you're trying to do this in a really short amount of time, ultimately what it comes down to is trust in your process and trust in the power of making regular progress, right? Those are huge things. All right, maybe I'll do the next one for the sake of time. Why is using the process bad? This is probably nobody else will talk about why process is bad. Process is almost always good. The problem is that process, even something like Agile, which is supposed to be lightweight, blah 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 blah, it'll always cost you overhead. Usually that overhead cost is minimal and it's going to almost always be worth it, but it is still there, right? There is still a little bit of a price to find a process. But really that's the only kind of major downside. Now, the reason why we're going to use process here for problem solving, right, this ADJ thing, is because we want two things. One thing is we want consistent results, and the second thing is we want to make sure that we're able to tackle really hard problems. Because a lot of times what happens is problems that are difficult either because either I've made them difficult or they're maybe real world problems. They're really hard things. Well, the issue there is basically you don't know where to start, right? The problem somehow is too intimidating. So how do we address that? We address that by having this fixed steps we go through. So it's like, no matter what I'm looking at, I'm going to start with our analysis. I'm always going to have a way to get started. And hopefully if I always do the same thing, no matter what problem gets set my way, I'll be able to crunch through it, right? So that's what we're going to be doing that here for problem solving, which I think is a little bit different. They normally don't really talk about process and problem solving textbooks. They usually kind of, well, they do, but they don't talk about it with engineering stuff. But we'll use it here, right? So that we kind of don't, we always have kind of a way to make progress, if you would. All right, so another engineering topic here, the idea of patterns. So patterns are something else that's kind of essential in engineering. Some of the idea is that you're not the first person to have seen your problem. Someone else has already seen it and they've solved it. And maybe probably solved it better than you can solve it because they were experts, right? And they had all their life to figure it out, right? You're a newcomer, right? So typically what happens is people have already solved a lot of common problems that are out there. And so what they do is they build a solution to it that can, be reused, right? We want to have a reusable solution that I can kind of, save time by, that I can use to save time because, hey, it's already done for me, right? I need to basically just see that this is already solved and I can use their answer, right, in whatever I'm doing. You guys may have heard the phrase a little bit before. I think you guys probably have heard like the phrase design pattern before. You guys just put like a check marker next to my screen. I need to clear those. You guys have probably heard, right, design pattern before. They'll probably talk about it at some point in like SER222. But yeah, that's kind of a thing, right? So let me see, I can do yes over there, no over there, right? So they have basically these big books of design patterns, which basically are kind of like typical software problems, and how can we possibly solve them, right? That's actually a thing. So yeah, again, like this is something actually that problem solving books don't really talk about if you go and try to find a book about problem solving, but there are you can basically have a huge volume which has a list of all these different techniques for solving problems, and it tells you like when do you use this technique to solve a problem. When is it appropriate? When is it not appropriate? What leverage does it give you? Maybe if it's not appropriate, here's some other patterns that might be useful, right? How much time does it take you to solve a problem using this approach? How hard is it to use, right? All these things, right? So you can actually sit down and basically make a list, right, of all these different techniques for solving problems. Here, there's a little excerpt here. This is for elimination. You can read it if you want. Elimination is a way to solve problems. You can sit down and quantify them, right? Because, the patterns by which people solve problems, those are kind of a consistent thing, right? We always solve problems a certain way, right? So why not write them out? Why not codify them? Why not just, make a recipe for them, right? That lets us kind of know what we have available, right? So that we're looking at a problem, we can be like, oh, I'll use this approach or that approach, right? So yeah, so that's just kind of a note that's about patterns in general. And then these are problem solving patterns. You guys, I may or may not give you guys some patterns for problem solving. We'll have to see. The problem is that it's not in any book, so I have to write them all myself, which takes a lot of time. So yeah, This is an excerpt from me from something else. So yeah. All right, so I think we're out of time. So let me just kind of give you guys a little idea where we're going. So we'll definitely pick this up next week. I don't know if I'll complete it in one day. I'd like to complete it in one day next week. I don't know if that'll happen. But basically, kind of up next, we're going to talk through ADJ. We're going to do it basically for the different, the different. Come on, give me. For the different, we'll do basically the different steps for the same problem and see how things kind of come together. All right. That's all I got for now. Any questions you guys have really quick about anything we're doing right now? Still no news about the exam. We're still waiting for AC to get back to us. Anything you guys got, or we'll go ahead and call it a day here. All right, so sounds good. So that brings us to the end of the day. So I'll see you guys on Tuesday. We'll do again live lecture next week. We'll finish up the ADJ stuff, and then we'll get back to programming with binary search trees. All right, so until then, have fun. We'll see you guys later.
Thank you.